Starting our second unit in SPH4C, grade 12 college prep physics, and it's called mechanical systems. So by the end of the unit we talk about different types of machines and torque and doing some calculations around that. To start the unit though, we're starting with one of the most, we're starting with studying some of the different forces, and of course this lesson is on gravity. And gravity, one thing that I want you to get out of this, even though it's not necessarily that practical, is that we feel gravity as the force between us and the ground and the earth. However, the truth is that there is gravity between any two objects that exist, including you and your pencil, or you and the person beside you. The thing is that because our gravity towards the earth is so huge, like the earth is huge compared to anything else near us, so because that's so huge, we don't notice the force of gravity between you and your pencil. However, if you were in outer space and your pencil was, placed 2 meters away from you, you would actually be pulled towards each other. You and your pencil would, because there is a force between you. It's just that it's small compared to all the other forces. But if you're in outer space where there's no other forces, no other big masses, you would notice that attraction. So, just some interesting gravity points. The first one is, and I suppose this is maybe the most important thing, is Sir Isaac Newton is the first one to really study and understand gravity, and it's called Newton's law of universal gravitation. And what he found is that not only does the Earth pull us down, but we actually pull up on the Earth a little bit. It's just fairly unnoticeable. Okay, gravity is, of course, what causes us to circle the sun. The Earth to circle the sun, and gravity is what causes the moon to circle us, and it causes the sun to orbit the center of our galaxy, because of course we're just one little bit on the arm of a galaxy of hundreds of thousands of stars. I think I should say billions, but I can't remember offhand how many stars are in our galaxy. It might even be in the billions range, but we're just one planet by one of the gazillion, let's just say gazillion stars in our galaxy. And our sun, which we orbits around the center of that galaxy. I think it takes about 250 million years for the sun to orbit the galaxy. And you might know this too, that because of the gravity, the moon has acts on Earth. We only really notice that. We don't feel it, but the tides do. And of course that's what causes our tides. So, the idea of gravity is a fundamental force. What does that mean? You might remember me talking earlier about the idea that there's actually only really 4 forces, and then every other force we ever talk about is just sort of a subset of one of those forces. And gravity is actually the weakest of them all, though we see it as something very strong, because if the Earth disappeared, like, we would be severely affected. But the reality is that gravity is very weak, and my best example of that is the fact that the reason you might remember that from chemistry class, that the atom is mostly empty space. Every single atom that exists is mostly just not air, it's empty space. It's less than air, right? But then you might ask, well, if that's true, how come any two objects can rest on each other? And there's really 2 reasons why that's true. The first, why 2 objects rest on each other. The first one is that the first reason is that like, there's an electrostatic repulsion between your electrons in your body and the electrons in the floor. Those electrons repel each other. That keeps us from falling through. And the second one is the idea that all electrons and atoms, but the electrons especially inside the atom, they whiz around really, really, really fast. And when you picture a fan blade, if the fan's not turned on, there's lots of empty space, right? But as soon as you turn a fan on, all of a sudden you've got this spinning, and it's like it's a solid. And that's kind of like what at the empty space that is our existence, that are all atoms in the universe is. It's like they move so fast they kind of appear like they're solid. Anyway, so gravity, though, compared to everything else, is very insignificant, because we should fall through the center of the Earth, but it's electrostatic repulsion that stops us. Let's keep going. Albert Einstein did a lot of study on gravity, and the work he did, it's called general relativity. It's way beyond the scope of any high school course. It's very, very complicated. But what he did say, and we don't have to study it, fortunately, is that space isn't as constant as just, what we think of as space, as geometrical space. All space curves, and it curves around objects with great mass. And so the picture, this isn't quite right, but imagine this picture of the Earth. It's like the space around the Earth is dented because of the Earth in it. And the idea, the visualization is supposed to be, you have holding a sheet, you drop a rock in the middle of that sheet, the sheet sinks, and that's this idea. And then the idea is that, say the moon, for example, it falls into orbit around us, or any other object gets sucked towards us, the Earth, because of that dent. And that's sort of the easy way to understand it, and we don't need to understand it at any depth beyond that. So Sir Isaac Newton did most of the work that we study in high school, and including gravitation. And he really was the first one to realize that gravity was more than just, an apple in the Earth. He's the one with the famous story of the apple. He also realized, though, that all objects, and we can calculate that. So he made some observations, and the first one is that, this looks confusing, but don't worry about it too much. It'll come out in just a simple equation. But that if you have two objects and you multiply their mass by each other, the bigger that product is, the more gravity force there is between them. Which kind of makes sense. It's just saying that the heavier objects are, they'll have more gravity. Okay? And that's what this sign here is, a sign that means proportionality. And it means gravity is proportional to the product of the masses. Okay? He also observed that the further apart two objects are, the less gravity there is between them. And it wasn't a straight line. It's not as simple as that. It's by the radius squared on the bottom. R is the distance between objects. So, in other words, what I'm saying is, a great example would be the sun is huge. It's massive, right? Way, way bigger than the Earth. Like about 1,000,000 times greater than the Earth. Okay, that's how big the sun is. 1,000,000 times bigger than Earth. However, we don't notice the force of gravity between us and the sun. The reason is we're so far away from the sun, whereas we're so close to the Earth, right? If we are as close to the sun as we are to Earth, if you could actually stand on the sun, which you can, we burn up, whatever. But, imagine you could, you wouldn't even be able to lift your feet. We're not strong enough because the gravity of the sun is so huge. But we're so far away, we don't even notice it. And that's really what this says, okay? And where I'm getting to is an equation. He found that if you combine those effects, you could actually get a straight line. And what that means is there's something called a constant of proportionality, and that's the slope of that line. Again, you don't need to worry about any of these details. All I'm saying is that we're going to end up with an equation. This G, so here's the number. You know why I asked you to learn scientific notation, right? Scientific notation number, and it's got these wicked units, okay? This is an important constant that we're going to use. The units look like it's confusing, but really when you do calculations, you just ignore the units anyway. So don't worry too much about it, but you are going to have to be able to punch this scientific notation in your calculator. Okay, so here's the equation that's the sum result of Newton's law of universal gravitation. That you can find the force of gravity between any two objects of mass 1 and mass 2. So the two objects could be you and your pencil, whatever. By multiplying those two masses by that G, here's G right here, and dividing that by the center-to-center distance. And we give the symbol R to center-to-center distance. The reason is when he made this gravitation, he was thinking of planets, and often that's reflected on the radius of the planets. But anyway, so center-to-center distance squared. And so let's just do a little example of that. We got Bert and Ernie. So there's a force of gravity between Bert and Ernie. Here's their two masses. Okay, we know Bert's 21 kilograms, Ernie's 26, and they're sitting 2.2 meters apart. That's their center-to-center distance. So what that means is, I know G, that's always the same. You should write that on your formula sheet. The center-to-center distance, 2.2. Here's the mass of Bert, here's the mass of Ernie. The things that are important, I suppose, is this has to be kilograms, and the distance has to be meters. Okay? And then there's the formula we're going to use. We're going to calculate gravity. And so, you should write this down, and you should practice putting your calculator. In fact, I might come by and check you put this very one in your calculator, just to know that you know how to do this properly, because scientific notation and all this stuff, it's easy to make mistakes. So here's what you get. you take this number, here's the two masses on top, right? Gravity, mass, mass, divided by center to center distance squared. And there's your number, 7.5. See how small it is? And it is small because you know that because I'll quickly tell you the gravity between Bert and the Earth is about 220 newtons. And here's the gravity between him and Ernie. And that's why Bert does not notice Ernie. It's too low of a force. This is tiny, 0.000000075, right? Okay, so is there an easy way to calculate gravity? There's a really easy way. And the reason is we usually neglect the idea of center to center. The only gravity we really concern ourselves with, especially in grade 12 college prep physics, is force between something, an object of mass m, and the Earth. And the formula is so simple. It's mass times g. And we talked about g in the last unit. Okay? So what I mean is this. Here's an example. Say I've got my coffee cup, and it's 500 grams. And I want to find the force of gravity acting on that coffee cup. Well, I have to put the mass in kilograms. So you take the number and divide by 1,000 to go to kilograms. Okay? And then I just go mass times 9.8. 0.5 kilograms times 9.8, and that's the force of gravity acting on my coffee cup. Okay, 4.9 newtons. Pretty much because 9.8 is so close to 10, just in your brain, just multiply by 10. Okay, here's another thing that's important, is the concept of weight. You're going to forget this, I know. However, I test you on this. Weight and mass are not the same thing. I know we use the terms interchangeably, but they're not the same thing. Weight is actually, in the physics sense, and in physics class, weight is force of gravity. Mass is mass. Mass is your weight, is your weight. I screwed that up. But mass is what comes out on the scale. It's, if you're 150 pounds, your mass is 150 pounds. Put that into kilograms, your mass might be, 70 kilograms or something. Okay? And that's your mass. It doesn't matter if you say it in pounds or kilograms, it's just mass. But weight is always measured in newtons. Okay? So the weight of my coffee cup is 4.9 newtons, while its mass is 0.5 kilograms. Okay. Two more, just a couple of quick things here. G, we call is the acceleration due to gravity, and that's true, but it also has the term gravitational field constant. And what that means is it tells us how much force 1 kilogram mass object would feel if anywhere, but in our case, near the surface of the Earth. And what I'm saying is, if you held a 1 kilogram mass in your hand, the force pushing down, the force of gravity on that 1 kilogram mass would be 9.8 newtons. But depending on where you are in the universe, G is not 9.8. It's only 9.8 at the surface of the Earth. If you could move yourself onto the moon, it'd be a whole different number. If you could be on the sun, I think on the sun, where on Earth it's 9.8 newtons per kilogram, on the sun it's about 295. Significantly, the 25 times more force. And 1 kilogram would feel, and that's why I said you wouldn't be able to lift your foot. 25 times more force of gravity. You have great thighs, I guess, from walking around. Okay, so just calculating gravitational field constant, and don't bother yourself too much with this, but you end up with, basically this is the equation right here. I'm circling it right here. The equation to find the gravitational field constant at any place in the universe is this, okay? This is how we come up with it, but the important piece for us is the equation. So let's just use that equation. That's the last thing we're going to do in our note today. Let's calculate the gravitational field constant on the moon. Without looking at the answer, you should know, or you might know, that it's smaller than Earth, right? Where on Earth it's 9.8, it's going to be something smaller. And here's how you find out what it is. Here's the 6.67 is the G. The M is the mass of, in this case, the moon, right? So if we're finding on Earth, you'd use the mass of Earth, but it's the mass of the moon. And this is the radius of the moon. And that's sort of why the R, by the way, right? Because you're talking about the surfaces of planets and such. And you put in your calculator, you should get 3.38. If you're looking at Jupiter, I think it's 27 or something like that on Jupiter. So again, significantly bigger, and the moon significantly smaller, and 3 times smaller anyway. But anyways, that's the end of this lesson on gravity, and it's fairly new concept and you might need to practice some stuff. I will definitely come by in the next day or so and just help you and watch you first, and then help you use either this equation or the FG equation. Just, being able to work with the scientific notation and dividing by the square, and there's lots of room for error, and I don't actually want to see you do it in your calculator, so when it comes to test day, you're successful on that. You don't mess that up in your calculator. Okay, that's it.